So the next speaker is Professor Jacques Magnaudet. He is a senior researcher at CNRS, the French National Center for Scientific Research, and he's working at the IMFT, the Fluid Mechanics Institute of Toulouse, the south of France. He is currently an associate editor of the Journal of Fluid Mechanics and also the International Journal of Multiphase Flows. His research focuses on several fundamental aspects of hydrodynamics and turbulence in two-phase flows and inhomogeneous fluids, mostly studied by means of computational and theoretical approaches. I welcome you, Professor Magnaudet. The floor is yours.
Okay, thank you very much. So, can you see my screen now?
Yes.
Yes, okay. So I still have to put it in full screen, presumably. Is it okay?
Yeah.
Okay, so very good. So I'm very pleased and honored to participate in this meeting. And actually, I've been knowing Bala, I think, for more than 20 years now, and we always have been in close contact since then. And it's impressive to see Bala becoming younger and younger, as Rama suggested, and even more prolific now than he was two decades ago. So congratulations, Bala, and I am really happy to be there. And I hope we will shake hands in the near future, not at the APS meeting because I will not be there, but in the near future at least. Okay,
Thank you.
Yeah, so today I decided to speak about the interplay of a pair of rising bubbles in the situation where there are releasing lines. And this is joint work actually with my colleague Jie Zhang from Xi'an Jiaotong University. So a little bit of introduction, of course. So as you presumably all know, buoyancy-driven bubbly flows are encountered in a wide range of applications. So be it in nature, for instance, in breaking waves or in volcanic eruptions, or of course in engineering, because bubbly flows are used in chemical engineering operation, especially bubbly columns. They are also used in power plants because boiling flows are used to cool reactors, etc. They are involved to steer liquid metal in ladle steel making, etc. And of course, they are involved in some inspiring liquids we will probably deserve in a moment. So it has been recognized now for quite a long time that in this buoyancy-driven bubbly suspensions, actually one essential building block is made of pair interactions between two neighboring bubbles. And this has been recognized both from experimental results and computational results obtained over the last 2 decades. And clearly, well, this building block plays a key role in determining the microstructure of the suspension. And this is why I'm going to talk about what happens between two bubbles. And so, of course, considering two bubbles, there are two extreme, let's say, configurations. One is the inline configuration in which the line of centers is aligned with gravity, and the opposite one is the one in which the line of center is orthogonal to gravity. This is a side-by-side configuration. So if we look at the predictions of potential flow theory in these two configurations, what this theory tells us is that, for instance, in the inline configuration, there is a pressure maximum in between the two bubbles, and so this yields, of course, a repulsive force. Conversely, if we look at the side-by-side configuration, of course, because the flow is accelerated in between the two bubbles, there is a pressure minimum there, and the two bubbles are attracted toward each other. Of course, there is a limiting configuration, let's say a critical angle, beyond which well, the interaction shifts from attractive to repulsive, and this critical angle actually varies depending on the separation between the two bubbles. But okay, so this is a simple view based on potential flow theory. But what happens as soon as viscosity comes into play is that, of course, there is a wake developing past each bubble. And because of this wake, actually, in between the two bubbles, for instance, there is a pressure gradient with a pressure minimum at the back of the leading bubble and a maximum at the front of the trailing bubble. And because of this, actually, there is an attractive force due to this finite Reynolds number effect. Similarly, in the side-by-side configuration, actually, there is vorticity generated about each bubble, and the two vortex fields interact and form a vortex dipole. And because of the sign of the vorticity in each leg of this dipole, actually, this yields a repulsive force. So in both cases, you see that the potential flow interaction force and the finite Reynolds effect interaction force compete with each other. They have opposite signs, and because of this, of course, one can anticipate that there may be an equilibrium separation distance between the two bubbles, which of course will depend on the Reynolds number. So of course, we have no proof at all that the corresponding equilibrium situation is stable. And to look in more detail into this stability and the resulting configuration, we decided to use 3D fully resolved simulations to study what happens, let's say, in real life. And we focused on the inline configuration. So the inline configuration, you see it here. So basically, we consider two bubbles with the same radius r and an initial separation S naught, and the line of centers aligned with gravity. So in this configuration, there are actually 5 dimensionless parameters. One is the Galilei number, which actually is a Reynolds number based on the gravitational velocity scale. Another one is a Bond number, which Rama defined previously. It's basically the ratio of inertial effects over capillary effect. Then there is the dimensionless initial separation plus the density and viscosity ratios between the two fluids. But these two ratios are usually very small, so they can be removed from the list of parameters. And in what follows, I'm going to consider only a given value of the initial separation. So basically, all the results I'm going to discuss will depend only on 2 parameters, the Galilei and Bond numbers. Okay, so a few words regarding the numerical approach now. So this approach is based on the Basilisk open source code, which was probably described yesterday by Luc Deike already. So the only thing which needs to be mentioned here probably is that this code involves a very smart adaptive grid refinement technique by which the grid is automatically refined within regions that either cross the interface or contain high levels of vorticity, especially in wakes and boundary layers. So you can have a view, a partial view of the grids we use here. So you see the 2 bubbles here and there. Oops, sorry. And then you can see a zoom of the grid around each bubble here. And you see that, of course, the grid is strongly refined along the interface and also within the wake of each bubble. But on top of that, actually, we added another layer, let's say, of topologic-based AMR scheme in order to deal with the very thin films that can form when the 2 bubbles get very close to each other. And basically, what we require is that when 2 interfaces get very close, actually, there is always at least 1 cell which is entirely filled with liquid. So this is the case here. for this layer here, but you see here that the yellow cells contain both gas and liquid. So we prevent this by requiring that if this occurs, actually, each of the yellow cells is divided by a factor of 2 in each direction in order to maintain cells which are purely filled with liquid. And you see in this case how, for instance, the grid evolves in the gap as the two bubbles get closer and closer to each other. And you have a partial view of the grid. So this is, let's say, the leading bubble. This is a trailing bubble. And you see how the film in between the two bubbles is described here. Okay, so let's start with the results we obtain by constraining the two bubbles to remain in line. So these are basically axisymmetric runs, and we will see what we get from these axisymmetric runs, and then we will compare them with what happens with when we allow the 3D configuration to take place. Okay, so here is a view of let's say the state diagram we obtain. So this is a diagram which is plotted against the Born number on the horizontal axis and the Galilei number on the vertical axis. So the blue bubbles on the right are about to coalesce. You see that they are extremely close to each other, of course. And the red bubbles instead maintain a finite separation between them. And as you see, of course, going from left to right, that is increasing the Born number, makes the separation decrease, whereas going from top to bottom, that is increasing the Galilei number, makes the separation to increase. So in order to understand these features, actually, of course, we have to keep in mind that increasing the Galilei number, that's increasing the Reynolds number, makes, let's say, the potential contribution to the mechanism increase at the expense of the finite Reynolds number effect. And since the potential flow contribution tends to produce a repulsive force, of course, we can expect that increasing the Reynolds number makes the separation to increase. And this is, of course, what we see in the results. So now what about the effect of the Born number? Why does the Born number make the final separation to decrease? To understand this, actually, we have to keep in mind that at a clean, that is surfactant-free gas-liquid interface, actually, the tangential vorticity generated on the interface in the liquid is actually proportional to the local and interface curvature times the relative fluid velocity. And because of this, actually, of course, if the bubble deformation is increased, that is, if the Born number is increased, so does the interface curvature. And because of this, the vorticity created at the interface becomes stronger, and so does the wake, and so does the attractive effect. So because of this, actually, making the bubble more deformable makes the final separation to decrease, okay? So here is a summary of the results regarding the final separation as a function of the Reynolds number on the left and of the Weber number on the right. And actually, all these results may be encapsulated within the correlation in red here. That is, the final separation is found to increase with the logarithm of the Reynolds number and to decrease with the Weber number, as I said. And for instance, if you keep the Galilei number fixed, and then you decrease the Born number, that is, you increase surface tension, you see the final separation slightly increasing from this value here to the value here, which corresponds to the case of two spherical bubbles. Okay? So that's what happens if we constrain the two bubbles to remain in line. But now, if we release, of course, this constraint and run fully 3D simulations, here is what we get. So in this case, this phase diagram doesn't contain final states. It's just made of snapshots. But what you see again on the right, yes, are the blue bubble pairs which are about to coalesce. And by the way, you see that most of the time they do so in the head-on configuration, whereas on the left you see red and green bubble pairs, which apparently maintain finite separations. But what you notice is that in all red and green cases, actually, the bubble pair is not aligned with gravity anymore. That is, 3D effects are clearly present, and this is totally different from what I told you just before. And the reason why actually these 3D configurations develop may be understood by considering the stability of the axisymmetric configuration. And actually, well, the mechanism at play here is known for a long time. It was pointed out by Harper some 50 years ago. That is, suppose you slightly shift the trailing bubble from the axis of the wake of the leading bubble, as I did here. Then in the reference frame of this trailing bubble, the flow felt by this bubble looks like this. So it's a slightly asymmetric shear flow. And in this situation, with the flow, the relative flow going down, it's known that for spherical or nearly spherical bubble, actually, there is a lateral or lift force going, in this case, from left to right. So this force is tending to remove the trailing bubble from the wake of the leading bubble. And because of this, actually, the axisymmetric configuration is unstable. So this is the mechanism which is at play. And this is just a summary of the 3 regimes we were able to identify in the simulations. So again, on the right is the coalescence regime, which most of the time is axisymmetric. So I will not speak more about this regime because of the lack of time. So I will focus on the red and green regimes. So you can already see from this picture that basically the green regime, which I call the drafting, kissing, tumbling, or DKT regime, is a regime in which the 2 bubbles separate at some point, and each of them starts to follow a path which differs from the initial vertical path, whereas in the middle here, you see what I call the asymmetric side escape regime, in which basically the leading bubble goes on rising along its initial path, whereas the trailing bubble at some point deviates strongly from its initial path and start to follow a completely different path. So I will now comment in more detail on these 2 regimes. Oops. Mm-hmm. Oh yes, okay, sorry. So first of all, here is actually the phase diagram we obtained. So the green bullets correspond to the DKT regime. The purple squares correspond to the ASE regime, and the red triangle correspond to coalescence. So what you see is that basically the DKT regime is encountered for Galilei numbers of the order of 10, which correspond to Reynolds number of the order of 20, basically. But increasing the bond number beyond a threshold, which is, let's say, between 0.2 to 0.4, depending on the Galilei number, all bubble pairs are found to coalesce. But below this threshold, and for Galilei numbers larger than 12 to 15, we see the region filled with purple square, and this region corresponds to the asymmetric side escape regime. And by the way, what is interesting in this diagram is also to look at the inclined solid lines here, which correspond to given values of the Morton number. The Morton number is a combination of the Bond and Galilei numbers. And the interesting feature of this combination is that it depends only on the liquid properties. And in particular, the red inclined line here corresponds to water. And you can conclude that bubble pairs rising in water in this range of Galilei number will never coalesce, actually, because you see that all points along this line actually stand well below actually the critical Bond number. Okay, so let's have a closer look to the DKT scenario. So here you can see actually a series of streamlines about the two bubbles. So you see that the two bubbles get very close with the streamlines still axisymmetric. But at some point, actually, there is a small asymmetry that sets in the gap. So you see here the zoom in the gap. And you see that actually there is some asymmetry starting here. And after this asymmetry has grown during some time, here you see the two bubbles starting to tumble around each other. And after this tumbling is completed, actually the two bubbles start to rise along two different paths with their line of centers more or less horizontal. And of course, you see that this interaction takes place when the gap is very small, which means that this is really, let's say, a short range interaction process. And another important point is the top view of the path here. And you see that this top view is a straight line, which means that the entire scenario takes place within a plane, a vertical plane, actually. And well, I will not comment all these curves in detail, but maybe I will just say a few words about this one, which shows the inclination angle of the bubble pair as a function of time. So you see that the inclination, of course, is initially 0. The two bubbles are have their line of centers aligned with gravity, and then the tumbling takes place, and you see that after some time, well, the line of centers is actually getting horizontal, and the two bubbles rise side by side. I will maybe skip this one and jump to the asymmetric side escape scenario now. And so again, here is a view of the streamlines past the two bubbles. So only streamlines emanating from the right part of the leading bubbles are shown in order to make you able to appreciate the point at which the first of these streamlines emanating from the right goes to the left of the trailing bubble, which correspond to the point where asymmetry breaks down, actually. And so this takes place when the separation between the two bubbles is still large. In this case, it's typically 5 times the bubble radius or so, which means that the interaction process is now, let's say, a rather long range interaction process. So in contrast with what happened in the DKT case. And so what you see is that once axisymmetry has broken down, of course, at some point, the trailing bubble starts to bend, and then, of course, it escapes from the wake of the leading bubble, and the two bubbles again start to rise on 2 different paths. But here you notice that actually they maintain a significant inclination throughout their rise. And again, the top view of the path shows you that the entire process takes place within a vertical plane. So again, you see how the inclination between the two bubbles evolves, starting from 0. So it grows tremendously during the interaction process and then stabilizes in this case at an angle which is close to 35 degrees. But maybe more importantly, what you may see here in this graph is that, so this graph shows you the horizontal velocity of each bubble as a function of time. So the leading bubble actually keeps an almost 0 horizontal velocity throughout the process, whereas the trailing bubble, which of course has an initially zero lateral velocity, gets a very large lateral velocity during the interaction process. You see that actually this lateral velocity reaches a maximum which is more or less 40% of the rise velocity, which is very large. And then, of course, this lateral velocity goes down to zero when the two bubbles are separated. Okay, so I will skip probably that one and show you just what happens when the bond number increases and comes close to the threshold in this case. So you see that for a bond number of 0.4, then the two bubbles start to separate little by little, but they get very close in this case, but still the, the lift force is large enough to allow the trailing bubble to escape from colliding with the leading bubble. In contrast, if the bond number is increased slightly beyond the threshold value, you see that actually, well, the lateral drift of the trailing bubble slows down, and actually, of course, since the separation between the two bubbles gets smaller and smaller, in this case, actually, the trailing bubble is not able to avoid colliding with the leading bubble. And if we go on running this simulation, we will find that coalescence takes place. So this is actually what defines the threshold for coalescence. So all this was with a zero initial deviation. But of course, in real life, the initial deviation is never exactly zero because of experimental uncertainty or whatever. And so we also consider the case in which there is a non-zero initial deviation. And this case actually is fundamentally different from what I told you before. And the reason is that actually in this case, the initial configuration is already asymmetric. So no instability is required actually in this case to drive a 3D evolution. And as you can figure out, of course, as soon as the wake of the leading bubble reaches the trailing bubble, actually that trailing bubble faces a slightly asymmetric shear flow. And so, of course, no instability is required to drive its lateral drift. And you can appreciate the difference between the two scenarios here. So on the left, you see the phase diagram we obtained by letting the initial deviation be 2 degrees. And you can compare it with the phase diagram on the right, which corresponds to strictly zero initial deviation. So you see that on the left, there is no green bullet at all, which means that the DKT scenario never takes place. And you can also see that the threshold bond number is about 0.7 to be compared to what we got before with a threshold which was ranging from 0.2 to 0.4, depending on the Galilei number. So clearly, a tiny initial deviation makes the final evolution of the bubble pair very different. So I will run short of time, and so I will skip several slides and just give you a take-home message now, because of course here we concentrated on a single bubble pair, but of course in a real suspension you can imagine that, of course, each bubble as it rises will encounter another bubble at some point. So a new pair will form, and this is a self-repeating scenario. So what I described for a single pair will be repeated as time proceeds in a suspension. And this is why actually, of course, this pair interaction is a building block that, of course, drives the microstructure of a bubbly suspension. So if we think about the two scenarios, the DKT and ASC scenarios as these building blocks, Of course, DKT leading to side-by-side configurations imply that it promotes horizontal clusters, whereas in contrast, the ASC scenario in which actually depending on the flow parameters, that is the Galilei and bond number and the initial inclination, we saw that actually the ASC scenario results in bubble pairs with different final inclinations and different horizontal separations. And since this scenario is by far the most frequent, especially because there is a non-zero initial inclination in all real suspensions, actually this scenario favors a much more homogeneous distribution of bubbles in real bubbly suspension compared to what would happen with a pure DKT scenario. So this is, I think, the main take-home message. And with this, I thank you for your attention, and I'm ready to take your questions.
Thank you, Professor Magnaudet. One quick question from the audience.
Can I ask one?
Sure, sure.
Yeah, so Jacques, that was a lovely lecture. I just want to ask you, like, if you have something in between, you know, suspension and two bubbles, if you have just a row of bubbles coming out from one source, so then would this be a mechanism for getting a widening jet of bubbles, your side escape mechanism?
And so you are thinking about a line of bubbles?
Yeah. So I'm thinking about a source which is giving out bubbles at constant frequencies. So you have this line of bubbles. So are they going to spread out into a jet?
Well, they will, of course, because of this 3D instability and the fact that they will not maintain the inline arrangement, actually. And we also looked at that in detail, and actually we showed how actually you can extrapolate what I showed for a single pair of bubbles to the case where they are released with a constant at a constant rate. Yes, but basically, yes, of course, the inline configuration will be broken down by this 3D instability, and then you will get an unstable jet and then a proof. Yeah.
Thanks.
There is one more question from Professor Bala. Yes, please.
Do we have the time, Vagesh?
You can ask a question. Yeah.
Okay. Jacques, wonderful talk. I have one simple question. In DKT, when you have particles, they do collide and then sort of bounce off. Here, how does it, I mean, I'm pretty sure that even bubbles can touch, but not coalesce, and sometimes coalesce. How does one approach that very complex problem? Same thing applies for droplets as well.
Well, maybe there are two sub-questions in your question. So it's clear that actually here there is never, let's say, a true kiss between the two bubbles in the DKT scenarios. That is, they always maintain a finite separation, even though this is a very small one. It's a finite one. So it's different, of course, with from what happened with solid particles. Well, conditions for lubrication are different, etc., etc. The boundary layers are much weaker here, etc. But so that's maybe my answer to the first half of your question. Then in cases where actually the two bubbles get very close to each other and we prevent the 3D configuration from occurring, actually in this configuration, coalescence always happen, and it has to happen actually because it's known that actually the van der Waals forces in the case of two clean interfaces separated by a liquid film, the van der Waals forces are attractive. Also, the hydrodynamic force in this case is attractive. So all forces are attractive. So unless there is a lateral deviation, all forces tend to make the two bubbles coalesce, and they will coalesce actually if we let the process evolve. Of course, in the computation, we have, for of course, reasons of computational cost, we have to cut the tracking of the thinning of the film at some point. So we observe a numerical coalescence which occurs too early compared to the physical coalescence, but indeed coalescence would occur also physically in this system. Does it answer your question?
Oh, that's a great question. I mean, basically, you're saying that the forces are such that if they come really close, they will merge. There's no other option.
Yeah, sure. Okay. They have to. They have to.
Thanks.